In section 12.5, we're talking about triple integrals. So let's just think back to where we got to up to this point. We started computing double integrals where we would do two integral signs, sum, f of x, y, dy dx, or dx dy, whatever we did, denoted some general dA for area. And when we talked about what that meant, we said that it's sort of like the volume under f of xy above some region R. And just to remind us what that looked like, if this is our x, y, z, you could have some random region R, doesn't really matter what it is, some surface f of x, y, and we said we were kind of finding the 3D equivalent of area under a curve is actually just this whole volume that fills up the space above R and below f of xy. So that's what we learned how to do in sections 12.1 and 12.2. I'm going to delete this picture because we don't actually need it. It was just to remind you how we talked about this idea. But now we're going to think about triple integrals. Over some, we'll do like D instead, and we'll do G. A function of three variables where we integrate over a volume. So for example, dv, we could write dz, dy, dx. Just this is a placeholder for integrate with respect to two variables in whatever order you prefer. This dv is a placeholder for integrate with respect to three variables, but it can happen in whatever order you like or whatever order the problem gives to you. And before we get into the details of how to compute these integrals, I know that some of y'all are visual thinkers, and so it's going to help to actually have an understanding of what this means before I ask you to compute it 20 times. So I think that there are two different interpretations that are helpful. We can hold on to the idea of volume. If we integrate just the function 1, we'll just do dz, dy, dx. That's just going to give you the volume of the domain specified by your triple integral. Just like when we had double integrals, if we integrated 1, it would just give us the area of the region R. But if we actually want to think about having that G in there somehow, we could say this is sort of like a mass if we assume that the function inside is the density at every point. So back when we came up with this idea of volume under a curve above some region, what's happening is integrals add a bunch of stuff up. So f has some height everywhere on our double integral. And so if we add up that height everywhere, kind of like if you have a box, and you add up its height at every single point, and you can do this forever because you're calculus, then that would give you a volume. Multiplication is a bunch of additions. That's something you learned in algebra. So when I say that we could integrate over some domain D a density rho, now it's saying our region over which we integrate is this whole box. But at every single point on the box, I know its density, like, grams per meter cubed. And if I could add up all those different densities for smaller and smaller dots inside this box, eventually I would recover the mass. Oh, that's going to be way too big. And so that's one possible interpretation. The last way that might help to think about it is as an average. So if you can find the volume of your region D, which you can using the first bullet point, then if you take the triple integral of any function over that region D and divide by the volume, you're going to end up with the average value of that function over the region you thought about. So kind of, you can imagine you have 3 inputs x, y, z, and some sort of function that takes on values. I actually can't draw it because it should change in x, y, and z. But something you want to measure that you care about that has 3 dependent variables, x, y, and z. Then if you integrate over some region, now we could say that this is the region of permissible values x, y, and z that you care about. Then you can find the average value of the output function over that region. And so whichever of these 3 things makes sense to you, just hold that in mind when we evaluate triple integrals. And I recognize that imagining triple integrals is difficult. This double integral hopefully matched your feeling of 3-dimensional space, but now you have to integrate over 3-dimensional space and imagine another thing in 3-dimensional space that changes. And that's really not a way we're accustomed to thinking. However, evaluating these integrals is not much more difficult than double integrals. So we've already done the hard part. We've learned how to take more than one integral before. Now we're just adding another one on. And so we're going to have our same strategy where you hold the outside variables constant. Integrate with respect to inner variables. And then move out to the next variable. For double integrals, your process would have stopped there. You integrate one variable and then the other. All that's going to change now is you integrate one variable and then the next and then the last. So the process itself shouldn't seem unfamiliar because it's the same strategy we used before. However, actually, I'm not going to write however twice. Just the most difficult part of these problems is the same as the most difficult part of the last problems. So figuring out what to put on these 3 integrals. is what I mean by setting the bounds. And that was the hardest part of sections 12.1 to 12.2. And as we go through the next practice problems, you'll see that it's the hardest part of this section as well.